Welcome to this first keynote talk. This is by Deb Hughes Hallett, who is a joint appointment at Harvard Kennedy School in Public Policy and Arizona in Mathematics. And Deb has been a leader in many movements in mathematics. She was very fortunate, I felt, to get to work with Andy Gleason at Harvard in calculus reform. And Andy was a remarkable individual. And she's going to be talking about the project that she's most involved in now, Data-Driven Visualizing the Future is her title. After this talk, we have a full hour of breakout where we can chat and talk in more detail. But if you do have a pressing question, we're monitoring the chat, and we could interrupt and bring that. So she's now not in Cambridge, but she's in Phoenix enjoying the warmth while the rest of us are enjoying the cold, or are in the cold at least. So I'll turn it over to Deb. Thank you.
Thank you very much. I'm actually in Tucson. It's
Tucson,
a different place.
No, I know that.
It's a different place. Okay, Brian, thank you very, very much. And yes, I have been very fortunate to have worked with Andy, who was an amazing person to work with. I also want to say thank you, since he's online, also to Enrique Acosta, who is joining us from Bogota, Colombia. He was a graduate student at the U of A, and I had the great fortune to meet him there. And he's been in touch with us ever since. And he has played a significant role, some of which you'll figure out, with what I'm talking about. So thank you, Enrique, for being here. Okay. And everybody else calling in from all over the world, it's wonderful to have you. I'm going to talk about what I think math departments and perhaps statistics departments, data engineering might want to think about in the near future about how things are changing. Okay. In particular, I'm going to talk about data, but I'm going to talk about data used in our courses. Now, I'm fully aware that this is a conference on differential equations. I hope, Brian, you won't mind. I'm going to take the liberty to talk about data-driven mathematics in a range of courses. It includes differential equations, but it's not only that. Okay.
That's great.
Okay. Think about our students as of today. Where are they going? Well, all over the place, but one particular new place that they're going is data science. I don't know about for you, but for many, many departments in the US, data science has become a new big major. Okay. And I want to think about what effect that might have, should have, could have on the rest of us. I also want to think about, because these go in parallel in my head, what issues students are concerned with, particularly outside of mathematics. Not because it isn't great to be concerned about mathematics, it is. But I want to think about how students are interested in other fields. I would put climate change and, unfortunately, pandemics high on the list, and all kinds of inequality, whether it's economic inequality, racial inequalities, and so on. You may have a different list. We do not need to share the lists, but I want to figure out how to include significant issues outside of mathematics into mathematics courses. As a backdrop, thinking about the data science part of it, there's a slightly odd quote about exponential shortages. I'm not completely sure that's a correct use of exponential, but whatever. Data is a big deal. And at the moment, quite what it takes to be a data scientist is in flux. But I think that training people so they have access to the huge number of data science careers is something we should keep in mind. Some great quotes about what it means to know about data. Without data, you're blind and deaf and in the middle of a freeway. They're somewhat right. And I will try and give some littler examples that one might do in classes in this talk. And then in the hour afterwards, I want to hear your ideas and what you think we can do. Just a moment. So here's a perspective on statistics and data science majors. This may not apply exactly in your university, but it applies in many. This is the University of Arizona. That's where I am right now. And notice our math majors, the blue line, have some of them migrated to data science. Now, data science is in our department as well, so they migrated inside the department. But I think we all want to think about how to accommodate this interest. Okay. And you can see the numbers at the bottom. It's a new major, but it's grown very fast. Why is this happening now? Well, take a step back and think about it. Data on the internet has become very prevalent and much easier to get at than in the past. It used to be that it was hard to download, it was buried in a PDF file and beastly to get out. Now open data is actually quite common. Shouldn't our students be using it? I think they should. Also, computation has changed massively. That makes a huge difference. Statistics, depends on when you were growing up, used to be a rather difficult subject in which all the data was made up and was polite numbers between 1 and 10, because you couldn't add anything else. And now real data is eminently usable. So what I want us to think about is how we should respond. I'm assuming that we should respond. I think for mathematics, not to respond is a mistake. Now, you may feel differently, but I feel quite strongly that we need to involve data in our current courses. Okay, so now I'm going to give some examples. And here are the principles that I'm thinking by, just so I'm trying to be upfront about what exactly we're doing. I personally want to use data about global challenges. Okay. The ones I'm picking, you can pick different ones, are the climate and the pandemic. I've also done some work with inequality, but that's not in this talk. I also think it's important that data tells a story. Say, wait a minute, I'm not teaching writing, I'm teaching math. Okay. I think linking the data to the real world and having it tell a story is very important, both so that our students can communicate with people that they meet as professionals, and also because it involves students. It shows that what we're doing can be important to them. So telling a story is very important to me. And the computation, I think, should illustrate the story, illuminate the story, not just be work for the sake of work. This is actually a very high standard to put on the data you include, because it's pretty hard to do all of these things at once. Teach good mathematics, tell a story, and illuminate the story. But that's what I think we should try and do. Computation, I think, can be very, very differently applied in different places. So I'm going to show things mostly made in Excel. Google Sheets, R, Python, symbolic manipulators, all fine. How you do it varies from place to place, but the idea of doing it is very similar. Why should we move this way? Because the world is moving that way. Data is creeping into everything. Mathematics, if it doesn't move, will place itself solidly on the sidelines. In addition, students, if they don't see us using real problems and real data, to some extent disengage. So I think both for our students and for our departments, that's important to do. So I'm going to do two types of examples today. One is on climate change, and one is on pandemics. In particular, a well-known pandemic, COVID-19, which has upended our lives for the past couple of years. Here's climate change. Big picture. I think it's important to think about the difference between climate and weather. I also want to make the case that climate, and for that matter, pandemics and different aspects of it, are very politically fraught at the moment. You might think, oh, I don't want to get into this. I think that mathematics has an important role to play. The data is the data. In some sense, no matter what side of all the political divides you're on, I agree that different people may have different ideas of facts, but climate change involves global warming. You can check that the temperature is going up. It does involve melting ice caps. It does involve sea level rise, flooding, and more severe storms. I think having us use the data, not to push a particular point of view, but to just look at the data and see what it's telling us, is actually very important thing that we can do, mathematics can do, to help the debate. It's also true of pandemics. Looking at this, the first thing to understand is that we're looking at climate change, not weather change. So an anecdote about it snowed a lot this year, yes it did, doesn't tell you what the climate is doing. The climate is a long-term issue. Some students understand that, some don't. It's important scientific point. Now to the specifics. How do we know carbon dioxide is increasing? That's something which we are fortunate, we as the world here, we are fortunate to know way back to the 50s. This is actually an extraordinary example of how an individual person, who at the time was considered probably quite nutty, has made a huge difference to science and the rest of us, because he started collecting the data in the 50s, when it was not commonly thought that global warming was happening, that anything was going on. So it's a miraculous story of a human being's foresight and contribution. This is where the original sets of data are still were collected in the 50s and are still being collected in Hawaii. This is an observatory way above the cloud level, and it's been collecting data for years. Beautiful place and remarkable contributions. At the bottom, and this is the part of the story, are the people who made the difference. The carbon dioxide level, and if you want to go and collect the data, there is the website. I will make available all of the websites for all of the data. Is called the Keeling curve. Why the Keeling curve? The people that you see in the photograph are Charles Keeling on the left. He died in 2005, but he was the person whose, at the time, slightly bizarre determination to collect carbon dioxide got it all started. And it went through to the present day. It's an enormously valuable set of data. His son, Ralph, is on the right. His son, Ralph, is alive and working. And he is collecting similar data. Actually, he works particularly on oxygen. They are a remarkable family. And it's also nice to know that they are two of the most humble, nice human beings in science. So they deserve every piece of praise that I would like to give them. Let's look at some of the data. What could your students do? So this is the data. It was downloaded from the site I showed you. And I've just put it in Excel. You can put it in whatever you want to put it into. And the blue is the data. What is the red? The red is the least squares line. So this is curve fitting. If you're doing statistics, you can look at this statistically, which we won't here, but it's perfectly possible. This is not a differential equation, it's quite right, but it is useful mathematics. You can also see, look at the red and the blue, that the linear function doesn't fit very well. The slope is too big at the left-hand end, that's in 1950, and too small at the right. What is that telling us? It's telling us that the rate at which the carbon dioxide is going up is increasing. This is not bad, this is not good. There's a lot of mathematics in being able to interpret those coefficients. And it can be done in Algebra 1, in Algebra 2, in college algebra. Here we are fitting an exponential to the same graph, to the same data. It has the alarming effect that you see the exponential doesn't fit very well either. It was too slow at the beginning and too fast at the end. It's not growing exponentially either. It's growing faster. That has real alarming, yes, so in the chat, people are making comments. This is where the thanks to Enrique comes to play. He just wrote a problem, which what model does fit better, okay? And Jean-Marie is on the right track. It is higher than exponential, and we're happy to give you, or Enrique is happy to give you a question that you can give students along that line. And this has really alarming prospects for the future. Okay. I'm going to say a brief, tiny bit here, but mostly I'm not going to do this piece. One thing that's useful in a lot of modeling is looking at logarithmic scales, which I don't know, they aren't very often covered in the curriculum, but in the pandemic, as well as in climate change, they can be very useful. So here is Excel doing logarithmic scales at the top, and here I've just, here I have just taken the logs and fitted a line, and you can see that the the relative growth rate comes out the same in both cases. Going on. as I said, I'm calling you from Southern Arizona, and I'd like to encourage some of you to think of examples in your regions that make sense to your students and that you may have access to data for. Tucson, so we're right in the southern part of Arizona, close to the Mexican border, and it's quite hot down here in the summer. One of the things that happens is there is a competition. You have to guess in February, it's probably starting now, when it will first go over 100 at Tucson Airport. This is run by one of the TV stations, and they give a prize. What is the prize? It's an air conditioner. Okay. And they've been doing this for a while. So here is the data from the last century. So that looks like a mess. Okay. Yes, it does. Does it? Do you see a trend? Maybe. Okay, yes, there is a trend. If you're into statistics, this is actually a statistically significant trend. And what is it telling us? The date is coming earlier. Yes, because the slope is negative. Why is this? Well, it could be global warming. It could be who knows what. How quickly is the date moving earlier? About 0.9 days a year. About 6 days in a student's lifetime, assuming he or she lived to 70. Maybe I should have picked 80. At any rate, not huge, but it's noticeable. So I'm very interested in hearing local examples of this. There are plenty of other local examples. Alaska has some interesting ones. There was a wonderful story this year about climate change in Japan, where they have looked at the flowering date of the cherry blossoms, which, thanks to the emperors, have been kept since the 8th century AD. 8th century. Pretty impressive. Yes, thank you, Milena. Groundhog Day is a great example. I would love somebody to do that. That hasn't been done yet that I've got, but yes, super example. One more climate change example, and then we will go on to pandemics. Here's another type of example. There is going to be, not in Tucson, but in many of the places that you live, there is going to be significant disruptions from flooding. We mostly think of them as sort of isolated disasters. Bottom left is Hurricane Sandy, Miami floods periodically. It's going to be more and more regular. And I think that our students, who are going to be the ones voting on this in the future, need to think about how to understand it, how to cost it, and how to think about it. Because they're going to be the ones who are voting on it. I think by the time this happens often, we're not going to be around, but our students are going to be voting, and it's going to be their taxes and their money and their votes that decides this. So I want to do, actually, this is a cheerful example because a lot of the others are not so cheerful, about a place that some of you may know in upstate New York. A number of places, actually Boston is one of them, are going to have to put aside money, and it's substantial money, for building seawalls or else. And let's look at this particular example. This might not look cheerful at the moment, but the next piece is cheerful. In Binghamton, New York, which is not on the sea, it's on a river, there's a hospital, which is a local hospital. So it's very important to the people who live in the region because it's the main hospital of the region. And in 2006, the river flooded. as an aside, for people who live near the coast and want to figure out how much danger they are in, the bottom right is a little map of Binghamton, and this website, which you'll have at the end, so you don't need to worry about it, is a great source of maps and shows you in rather clear detail what kind of disaster you are facing. Anyway, in 2006, there was a huge flood. This is the bottom floor of the hospital. It flooded quite a lot, and it was full of sewage because it came from the river. So it was awful. They had to move all the people in the hospitals, the people who just had heart attacks, the people who had grandmothers in there. They all had to move. You couldn't live in this hospital. This picture at the top right, that kind of arc, that's the emergency room entrance. It was totally flooded. People couldn't get in. It was awful. And it really happened. They decided after that, we have to spend some money and get this so that it works. So in the summer of 2010, so this is 4 years later, they built huge walls around the hospital. And the particular cost was a lot less than the cost of the flood, but still they had to vote it through, get money. You know, our students need to understand how this works. What happened next? Here's some of the planning that I think our students should do. This is an Excel spreadsheet where we're looking at present values. Now, wait, you say, wait a sec, I don't teach present values. What are they? Basically, mathematically, they're exponential decay. They're easy to do with the mathematics we do teach. Okay. It's not hard to do them. If you have a business program on your campus, they will love you for doing it. And you can do it in Excel or anything else. It's quite easy to do. And that's how you decide how much to spend and how to manage it. 2011, only a year later, they had another flood. Here is the emergency room entrance. The water was stopped by the wall. Personally, it looks terrifying to me if you're working on the ground floor here and you might be scared that the water would break through. I don't know. But there's an important story here, which is they planned well, they built well, and they preserved the hospital through the next flood. So my admiration to them. One last set of examples about the pandemic we're in. Now, I want to say a word about doing this because when I started thinking about the pandemic, I was worried, and the people I was teaching with were worried that somehow this would be too alarming for students, that they would find it depressing or scaring or whatever. And we did it anyhow. And some of you, particularly Brian, know this story. A year later, I was interviewing some of the students to be undergraduate assistants in the next time I did the course. And I actually said to them, is there anything I should never do again, or I should definitely do again this year? And one of them said to me, surprised to be asked, please do that COVID example again. It's very similar to the one I'm going to do here. I said, I'll be happy to. Why? And she said, it made me much less afraid. I said, really? Yes, because it showed not everyone would get sick. It showed how this worked. So if it's done politely and kindly and respectfully, students enormously appreciate mathematical models, even of things that are not good. It gives them a sense of being able to manage. That's very important. She's my assistant again this year, So she has seen what I'm doing. She's my advisor. Looking at some backdrop, I'll just show you a couple of examples. There are lots here, and in the breakout afterwards, if you want to see more of them, I am happy to share them. There are two data streams that are particularly useful. For each region, this particular one is Switzerland, we might look at the total number of cases confirmed up to and including some day T, and the newly confirmed cases on that day T. Okay. They both tell you important things. We've been working in days. You clearly can work other units, but basically daily time is useful. So here are two graphs. This is 2 years ago now. This is Switzerland at the beginning of the pandemic. And to get students thinking about what we're doing, I wanted to have them think about which graph is P and which is N. Not necessarily obvious to them, but I know from quite some considerable experience it's not obvious. Which is P and which is N? P is the bottom graph. The top graph is N, because N can go up and down. When we have an outbreak, it goes up. When we have a lull, it goes down. P never goes down. What's the relationship between them? Approximately, and this is clearly approximate, both P and N are discrete. Okay. But if you think about how derivatives are defined, delta P over delta T is N. So approximately delta dP dt, the derivative, is N. So while calculus depends a lot on continuity, real data pushes you into an uncomfortable land of thinking about approximations and rough estimates. But I want our students to think approximately of how dP dt is N. Okay, here are some examples that I probably won't show you most of because I want you to be able to have some time to breathe. One can show, this is Arizona's data again, that the initial outbreak in the first fall in Arizona was approximately exponential. How does one do it? Now it really is thinking about differential equations. Yes, it looks likely here. Here is N over P. What is that? It's P primed over P versus T. That would be a constant if it was exponential. Now you might say, well, that wiggly blue line is not a constant. That's true. But for all intents and purposes, in the land of approximate data, it's actually doing pretty well. You can also look at P primed over P, P primed versus P, which is N versus P. It's again approximately a straight line. So a lot of basic differential equations can come in through the COVID data. Back to log graphs for a minute. This is South Africa. South Africa comes in. They've played an important part, you'll see in a minute, in the COVID story. Look at the log graph. The left graph looks sort of vaguely exponential. I don't know. This graph on the log scale, look at that kink. What is that kink? That kink is a real fact. It's when South Africa introduced their first lockdown. Now, this is 2 years ago, but you may remember it was ferociously tough, really tough. Why did they do it? Because the daily increase had been 30%. That's this very steep part. And they got it down to 5% in 10 days. It was brutal, but it did work. And it shows up in the graphs. And here they are. I'm not going to go through this anymore. Calculus 1, graphs and derivatives. Do you do graphical differentiation? Yes, we do. Here we go. I've done this many times with classes. This is the logistic curve in Iceland, and it also happens quite well in Australia, New Zealand. Since I know there's somebody from New Zealand on and Australia on, you guys have done a great job, and it's been tough, I know. This is Iceland's data. How do you look at it? Much the same way as you do in regular math classes. You look at a phase plane diagram. And there is the parabola. And there is the logistic differential equation. Here's another phase plane diagram. P primed over P versus P looks like a straight line. Here's the differential equation. They come out slightly different, of course, but they're close. And they're both fairly close to what's going on in Iceland. Okay. One more example. This is a recent one. You may remember in November of last year, so not very long ago, there was a big panic because Omicron was coming on the scenes. And you may remember how it happened. Who found it first? South Africa. And South Africa and Botswana, actually it was South Africa did the science for it. And they told us about it in early November. What was the reaction? I know that you probably felt as I did, oh no, we thought we were leaving, but no, we're not. Okay. The US enacted a travel ban. It was there had been several travel bans. So this is not the first one. What happened on Southern Africa? This is South Africa. Planes canceled. Look at the despairing lady. What was the effect of the travel ban? I want us to think about it. This is an example that my students will do shortly. So this is Omicron coming in or not coming in to South Africa, to the US from Southern Africa. So the travel ban was for all travelers from Southern Africa, except for US citizens and permanent residents. What was the government hoping to achieve? I imagine that you felt, as I did too, oh, they're trying to, prevent us having an outbreak. They're trying to make sure it doesn't happen. They're reducing the size of the wave. The sort of feeling of, oh my goodness, let's, shore up the moats and try and stave this thing off. They're preventing an outbreak, maybe. Reducing the outbreak, maybe. Delaying the outbreak, maybe. I was in no way in a position to know, but this seemed like a natural reaction. Your students and my students can look at this quite easily with the SIR model. S is susceptibles. These are people who could get sick, infected people who are sick, and recovered people who are recovered. Now, I'm taking many liberties in that I haven't taken account of vaccination. I've just been looking roughly at the data. You can probably all do this much more precisely and better, but here is a piece to look at. What are the equations? So these are the standard SIR model equations. And I'm going to look at just the S and the I part, and I'm going to assume, in fact, that we're just looking at this. Okay. Here is looking at the results of the model. How did I model the travel ban? By restricting the value of I0. So I0 is just the Omicron cases. Now, there are lots of other cases, whatever, but I'm just looking at this. I looked at I0 equals 10, 100, 1,000, and 10,000. 10,000 would be if there was no travel ban, lots of people from Southern Africa bringing in Omicron. 10 is if you have a travel ban, but there are a few permanent residents or citizens who come back anyway, and maybe some of them have it. Here is the phase plane trajectory. So the S-axis is horizontal, the I-axis is vertical. And you say, wait a minute, what happened? There's only one curve there. What am I looking at? Where are the other curves? There's supposed to be 4. There really are 4 curves there. What does it tell you? Ask your students. What does it tell you? Pretty interesting. Pretty interesting. Now I'm doing a time series plot. This is the same data. There are 4 graphs clearly here, and the colors are actually, you can see the code at the right. So what is it? So the right-hand one is 10. So this is the one where you have the travel ban. The black one at the left is a free-for-all. You may notice there is a delay. Yes, there is a delay, but the maximum is very similar. The maximum is not exactly the same. This is in millions. But I think for practical purposes, although there's definitely a difference in the maximum, there's no difference in whether or not there is an outbreak or roughly how big it is. The outbreaks with this set of parameters are about 100 million. Now, you may have different parameters. So what does it tell us? Whoops. It tells us that, unless you can get the I0 down to 0, the ban delays the wave, but it doesn't prevent it or reduce it. With my parameters, the delay would have been a few weeks. Okay. It's important to understand, I think, that the travel ban, unless needed to get the hospitals ready, which is a plausible argument, did an enormous amount of international damage without achieving much. It was a reaction of fear, I think, and a need to do something. But South Africa, who had done excellent science and been very transparent to the world, felt, we did the science, and what did you do? You banned us. And to no purpose. I want our students to understand the numbers and the data. This is the end for this part. If you would like to involve yourself further, both with what we've done or telling us what you think we should be doing, both ways are quite fine. Our webpage is at the top, thanks to Enrique. And there's a page for climate change. There's a page for pandemics. We're happy to have other pages on other things. My email is here, and the website contact is there. I will also put the links for the climate change examples and so on in. They're actually up on the web on this web page. Let me stop here. I can see that Brian has come back on the screen, and I'm happy to hear from everybody in the next session if you would like to.
Well, thank you very, very much, Deb, for enlightening us. And I think those of us who have been fortunate enough to hear your message are realizing this is not your father's math class or your mother's math class. The conversations, the use of mathematical terms in support of social issues, the obvious care in examining data and looking at it is something that you want to encourage your students to do, whether they're in data science or not. I mean, it seems to me how to read the newspaper is as valuable for our general literacy students as any.
I totally agree.
Yeah, and you've brought that out. Enrique was saying that he's been teaching students who are coming to the University of Columbia who are weak, and he uses Excel and data and spreadsheets to get them sort of used to mathematical thinking. And so these issues are important, and it goes without saying that Deb emphasized things by speaking loudly and directly, and her face went right into the camera when she was speaking, for example, about South Africa's plea not to ignore what they've been doing, et cetera, et cetera. So it is emotional. And as she did point out earlier, people are sensitive and may have lost a loved one. You know, I mean, it gets right to the very core of their existence. And so you do think, and I've heard these conversations with others, should we be talking about this? And the answer is yes, we better, you know, otherwise it's swept under the rug. Why don't we just take a 5-minute pause and then transition, stay where you are. I mean, you know, keep this screen on and we'll just talk about things more. I will tell you that at 5 o'clock, we have 2 tech presentations. Then we have a break until 7. And then at 7, we really have a blast of rich programs for you. And it's going to be hard to choose, but choose the ones you think you really want now that you want to interact, and the others will be online in the long run here, so you can garner what you can. So let's take a big break here until for those of you who have an analog clock, until the big hand gets close past the first mark. And those of you who have a digital, until it says like 6 minutes after the hour, and then we'll engage in more conversations. Okay, so please feel free to take a break, look around, think of the programs you want to go to otherwise, and come back ready to talk.